Hi and welcome to High School Physics Explained, and today I would like to go through the 2016 HSC Physics paper, which this time of recording was held this morning. So I've gone through the exam and I want to go through the answers, and I'll start first with the multiple choice. So here we go. Question number 1. Some mobile phones are recharged at power point using a charge flat that contains a transformer. What's the purpose of a transformer? The key thing is it's a transformer. Thing is, a transformer, of course, transforms voltages. So in this case, we're trying to decrease the AC voltage at the power point. So D is the answer. Now, in case you might think, oh, hold on, a charger at a mobile phone eventually converts it into a DC supply. That is true, but we're interested in a transformer, and it is the job of the rectifier to change it from AC to DC. Question number 2. Westinghouse and Edison proposed methods to supply electricity to homes. What's the advantage in this situation? Well, clearly the transformers means lowering the transmission current, which reduces energy loss. So the answer is C. Question number 3. A region of space contains a constant magnetic field and a constant electric field. And how will these fields affect the electrons that is stationary in this region? Well, if we put a charge in an electric field, it will experience a force. But for a charge in a magnetic field, it'll only experience a force if it's moving, because F is equal to QVB. And of course, if there's no V, there's no force. So in this case, the only possible answer is C, because only the electric field will exert a force. Move on to question number 4. This is all about superconductivity. So we have a graph about 3 superconductors, and you have to determine which is the correct classifications of these 3 materials. Superconductivity was first discovered by a Dutchman, and he looked at that in terms of mercury, and that is a metal. Then later metal alloys were helpful, and then finally compounds. So the answer is A. Question number 5. Now, question for number 5 is a numerical problem, and you're required to work out the magnitude of the electric field. And of course, the electric field is equal to the voltage divided by the distance. In this case, the voltage is equal to 15 volts. The distance is equal to 5 by 10 to the power of negative 3. And when you do that calculation, you're going to get 3000. So that's the answer, D. And of course, that's newtons per coulomb. Question number 6. A thought experiment. A jet is traveling at 0.5 c this direction. Another train is traveling at 0.1 c, and you're asked to work out what is the speed of light emitted from the train's headlight as measured by a pilot in the jet. This is fundamental understanding of the nature of relativity, and that the first postulate said that c is constant for all frames of reference, so therefore the answer must be D. 1C. Question number 7. A magnet passes through a copper tube at constant velocity along the path shown, and a current is induced. Well, this is all about Lenz's law. So Lenz's law is that as this magnet goes in, you are going to get a current that opposes the motion. So since the south is going in, you're going to experience a south first at this end, which means there is a repulsion at this point. But of course, as it leaves, the north is of course leaving over here. And so now, of course, it will produce again a force that opposes the motion. So we're going to get a south performed here, which means an attraction. And therefore, you're going to get repulsion here, attraction here, and therefore the answer is B. Question number 8. So in this case, we're asked to find which sets of coils and magnets produces the greatest deflection in a galvanometer. And of course, the deflection here is all about the greatest change of flux per given time. So the question is which gives you the greatest responses? Well, the first thing you need to understand is that the more coils we have, the actual more current we actually generate, and so therefore that discounts C. The problem with this one here is we've got 2 magnets, but they're opposing each other, so they basically cancel each other out, so that cancels out this. So that leaves B and D as your answer, but of course it's about the rate of change of flux. Since this moves twice as fast, D is your answer. Question number 9. How does back EMF affect a DC motor? Well, back EMF means that ultimately is that you have your input voltage and you have a small back EMF which lowers the voltage, which therefore lowers the current, and therefore the lower current means you have a lower torque. So that means A is excluded. C excluded because it doesn't reverse the current, and D is excluded, leaving B as our answer. Question number 10. In a thought experiment, a train is moving at constant speed of 0.8 c, and a lamp is at the midpoint here, and there's a door on either side, and light will move in either direction, and since the distances here are the same, they should arrive here at the same time. Therefore, W and Z should open up at the same time. This is irrespective of the fact that the train is moving at 0.8 c. Since that's the case, then the only answer available to us is C. Question number 11. What is the wavelength in meters of a photon with energy of 3.5 electron volts? Well, first what you need to do is convert these electron volts into proper joules. So to do that, you've got 3.5 multiplied by 1.6 by 10 to the power of negative 19, which gives you the amount of joules totally that this photon has. Well, that of course equals HF. But F, of course, is equal to C over lambda, so that equals HC over lambda. So if you rearrange that particular question, you end up getting a value of 3.5 by 10 to the power of negative 7 meters, and therefore the answer is B. Question 12. So which diagram correctly shows the deflection of a cathode ray by a bar magnet? Well, the important thing here, of course, is that there is right angles between three variables: the magnetic field lines, the direction that the force of the charged particles experience, and the actual direction of the velocity of the electrons. So anyway, the magnetic field lines here are going into the page, they're coming out of the page here, they're going up the page here, and they're going down the page here. But you'll notice that the force here is in the same direction or in the same plane as the magnetic field lines here. And so in this case, my magnetic field lines are going up there, but my deflection is down. And in this case, my magnetic field lines are going down here, my deflection is also down. They can't be, they're always at right angles, so therefore C and D are excluded. Now in this case, the magnetic field lines are going in. The important thing is, of course, that the current is going in that direction or that direction because it's in the opposite direction of electron flow. And so if you use your right-hand grip rule, or right-hand slap rule I should say, then you should find that the only diagram that actually is consistent with that is B. Question number 13. It says, when light of a specific frequency strikes a metal surface, photoelectrons are emitted. If the light intensity is increased but the frequency remains the same, which row of the table is correct? Well, light intensity means more photons. And more photons means more electrons. And that means you get an increase in current. However, the frequency, of course, contributes to the energy. But since the frequency remains the same, the kinetic energy of my photons remains the same. And so therefore the answer clearly must be C. Question number 14. A satellite orbits Earth with a period of T, and an identical satellite orbits with a planet of Xerus, which is a mass 4 times of the Earth. Both satellites have the same orbital radius r. So how do you work this out? Well, the important thing here is, of course, is that r cubed over t squared is equal to gm over 4 pi squared. This is Kepler's third law. Now, in our case, r has not changed. So the question is, if t represents, in this case, the period around Earth, what happens if I increase the mass? Well, if I increase the mass, then this value has to increase overall. But hold on, if that increases overall, then clearly that this value here must decrease. And in this case, I've increased it by a factor of 4, but because of the fact that this value is squared, this value has to decrease by a factor of 2, which becomes squared. So therefore the answer is B. So question number 15. Which of the following statements correctly describes the effect of light in a solar cell? Well, all of this is about the photoelectric effect, of course, so that as long as the energy is greater than the work function, HF minus HF naught, then the electrons are emitted. And so what happens is, if we're talking about here in terms of solar cell, we also know that we have some semiconductor material. So the question is which statement is correct? So let's examine it. The light produces electron-hole pairs. Well, that is true in that as an electron is released, you are going to leave a hole somewhere because we are talking about a semiconductor here. The light causes pure silicon to become an N-type semiconductor. That's not correct. The light increases the potential difference across the p-n boundary. That's not what it's actually about, okay? And the last one, which seems right, but I'll describe to you why it's wrong. The light transfers energy to electrons in the conduction band of the p-type semiconductor. Well, in fact, if it's a p-type semiconductor, there are no electrons in the conduction band. So there's no transfer of energy to the electrons in the conduction band. They have to get into the conduction band in the first place. So the only possible answer is A. Question number 16. This is a little bit more difficult question, and as you can see, the last 5 questions are more difficult than the last 15 that we looked at so far. The cone of the speaker is pushed so that the coil moves in the direction shown. Alright, so we've got the coil moving in this direction. Therefore, relatively speaking, the magnet is moving in this direction. We got, of course, that's really important to understand, because as this coil moves this way, this is going to generate an EMF and therefore a current. So automatically, since we are physically moving this and creating a current, we know we are creating or demonstrating a generator. That's the first important thing here. But what happens is that how do you determine the current? Well, the current can only be determined by using understanding of Lenz's law. So if the coil is moving in this direction over here, then initially here what we're going to have is produce a south here, because it's going to try to oppose the south over here. Using that particular view, the current is going to go up in that direction, which means the current is going to go in that direction, which means the current is going to go from Y to X. Therefore, that's true. Therefore, the answer is B. Number 17. Alright, a projectile was launched horizontally inside a lift in the building, and the diagram shows the path of a projectile when the lift was stationary. So the projectile was launched again with the same velocity, and at this time the lift was slowing down as it approached the top floor of the building. So it's slowing down. What is happening here is the acceleration is changing. And if you attach yourself to your experience, when it's slowing down, the acceleration that you're getting is actually less than 9.8 meters per second squared. So you feel a little bit lighter as it starts to slow down. So what therefore is happening? Well, if the acceleration is a little less, what will happen to the ball? Well, first of all, the ball in this case, it's important to understand that the new path is what we're looking in, is that the ball is not going to be accelerating more, which is really what's happening here. And so therefore, A is ruled out. There's absolutely no reason why the ball will suddenly drop down like this, as if we're having extremely high acceleration. So that's not the case either. Question is it B or C? Well, to be B, you must basically have a weightless situation. For this to move at a constant rate, there must be no acceleration present. So clearly, unless you are in an accelerator which is clearly causing you to be completely having a weightless experience, a microgravity situation, that will be the case. But it isn't the case that you experience, so therefore the answer is C. Question 18. A motorcycle travels around a vertical circular path of radius 3.6 meters at a constant speed, and the combined mass of the rider and the motorcycle is 200 kilograms, and you have to determine what's the minimum speed at which the motorcycle must travel to maintain a circular path. Well, to maintain a circular path, then the acceleration due to gravity must be equal to the acceleration due to the centripetal force. So in that case, v squared over r must equal 9.8 meters per second squared. If this was greater, he would feel pushed into this, which is what we want. If this actually is less, then what will happen is he will fall down. He won't actually make it right around. So using that particular aspect, since r is already known, you can actually work out what the v is, and the answer will be 5.9, and therefore the answer is C. Question 19, and this is a bit more challenging question. You really have to think about this. Muons are subatomic particles which have at rest a half-life of 2.2 microseconds. When they are produced in Earth's atmosphere, they travel at 0.9999 c. During the classical physics, the distance travelled by the muon in its lifetime can be calculated. So as far as the muon is concerned, if the muon were to calculate the distance that they would travel, they would say their v, which is 0.9999 multiplied by 3 by 10 to the power of 8, multiplied by the time, which is in our case 2.2 by 10 to the power of negative 6 seconds, you would get approximately 659 or 660 meters at which they travel. So the important thing is that's what they think they move. So if muons have some sort of sentience. So the question is what would an external person experience? Well, first of all, let's say the muon's going to be traveling only 660 meters and their lifespan is clearly 2.2. Well, that clearly means only A and C are correct in terms of this situation. But as far as Earth's frame of reference is concerned, the lifetime definitely increased. Time dilation takes place. And so therefore that is true in this case. It's greater. It's not less than, but it's also a greater distance traveled. So as far as we're concerned, the muon travels a great distance, in fact quite a few kilometers, in order to get to the Earth's frame of reference. So therefore the only possible answer is A. And finally, question number 20. And this one takes a little bit of explanation. In the motor shown, the rotor spins clockwise as viewed from a point P when connected to a DC supply. Now I'm going to assume that if we have a DC supply, then what we have with the commutator here is we have a constant DC supply, but of course that changes direction like so because of the commutator, and we're dealing here completely with the coil, so that continues to turn in a clockwise direction. But what happens when we connect this particular motor to an AC supply? Well, the first part is positive, that's true. And so that it will turn in a clockwise direction. When this is in the vertical position, then the current reverses direction, but now it also reverses in this direction. So because of the commutator, but it's extremely weak current at this point in time. And so therefore it will turn, but it'll slow down to the vertical position, and then it will go in the opposite direction. It'll speed up, and then maximum, of course, is when the force is at a tangent to the magnetic field lines, and then we'll go the other direction for that component over here. So it literally will go halfway, then come back to halfway, giving the only possible answer D. Question 21. And you should know the questions from here on in get into increasing difficulty. So these questions that we start off with 21, they're not meant to be particularly hard. So let's have a start and looking at the questions. So question number 21A. Why does an orbital decay occur more rapidly for satellites in low Earth orbit than satellites in other orbits? Well, the basically thing is it's low Earth orbit. So if you know it's a low Earth orbit, you're going to see more experience of air resistance. The atmosphere, of course, takes a play, and of course air resistance will increase drag, and that will of course mean that the gravitational force Fg is going to have a greater effect, and so therefore it's going to fall in towards the Earth. That's basically all you need for part A. Part B, it says calculate the magnitude of the gravitational force that acts on a 50 kilogram satellite when it's 8,000 kilometers, and I hope you realize that this is in kilometers. You have to convert it to meters. So when you do this, you basically say F is equal to G m1 m2 over r squared. And when you substitute everything in, you get 6.67 by 10 to the power of negative 11. There's your G. Your mass is 50. Your mass of the Earth, which is provided for you, is 6.0 by 10 to the power of 24. And you divide that by the radius. In this case, it's not 8 by 10 to the power of 3, it's 8 by 10 to the power of 6 because it's in meters, and all of that is squared. If you do the calculations, you get 312 newtons, and that should give you a full 3 mark. And you're all asked to find the magnitude, so don't worry about direction. Question 22. When an alternating current is passed through a coil A voltage is observed, and the oscilloscope is connected to B. So basically you should notice that coil A has an alternating supply, so the oscilloscope will produce an alternating supply, though the current will actually be in opposition to A. So for example, if coil A is in this direction, then coil B will be in this direction. But how could a bar magnet be used instead of coil A to produce a similar pattern? Well, basically you should have a bar magnet and you say that you move it in and out. And that's basically all you really need to do to get it in and out. So if you say, oh, you have to move a bar magnet, that may only give you 1 mark, but you have to move it in and out so that you have a changing flux in opposite directions, so the EMF oscillates, and therefore you get an alternating current in the oscilloscope. Question 22 continued. A strong magnet is at rest a few centimeters above a metal solid disc made from a non-magnetic material, and the magnet is then dropped. And you have to look at this, and it says account for the shape. Well, you need to note a couple of things. First of all, this is nice and straight right here. And then we have a curve over here, and then it's 0. So to get the 4 marks, you need to look at all parts. Well, first of all, this magnet is going to start to drop, which means it's going to accelerate. And of course, if it's going to accelerate, we have a change in velocity, and that should be constant because our acceleration is equal to 9.8 meters per second negative squared. Hence, it's negative over here. That's important. And therefore, the change of velocity over time is that acceleration. That's constant. That means that's nice and straight. But of course, as it approaches the magnet over here, it's metal, this is going to experience a changing flux, which means it's going to cause a little eddy current, which is going to oppose it, which means it's going to start to slow down. So that basically looks at this fact there, and therefore it's going to stop accelerating, and hence the level here is 0. What's going to happen, of course, then it's going to slow down, and eventually the change in flux will be so great so that it will actually cause it to stop. And so what happens is it's going to slow down, it's going to stop, and so therefore you're going to get a velocity that decreases, but it's going to be not at a constant rate, because as it slows down, that's really important, as the disk slows down, the rate of change of flux changes, and therefore you're going to have a difference in this curve over here. So that accounts for that. And so you need to look at, for accounting the shape of the graph, you need to look at all 3 areas and tie it in all with the physics involved. So we've got eddy currents mentioned and Lenz's law mentioned. That's really important. And that's basically what you're accounting it for. Question 23a. It says explain the role of the deflection plates in displaying voltage changes applied to input of a cathode ray oscilloscope. So a cathode ray oscilloscope, of course, has a nice little grid like so, and very nicely drawn, and you're going to get a trace like this. Well, what's happening? Well, you've got an electric plate. So if you were to imagine this as a plate, you've got electric plates that are, in this case, which causes my electron beam to be swept from left to right. And so that's giving you that force. So this plate over here, which gives me a horizontal electric field, will cause it to sweep this way. But then I also have a electric plate in the opposite, which has an electric field that oscillates. So it's connected in this case to my input for my voltage over here. So that's causing my electron beam to go up and down. And so therefore that traces the curve like so. And so that you need to talk about. So explain, you need to say that the electrons, of course, are experiencing a force. Here it's due to an oscillation EMF, and so therefore going up and down. Question part B. The diagram shows the electrons traveling in a vacuum at 5.2 by 10 to the power of 4 meters per second entering this electric field. What's different here is in many exams in the past, these crosses have always represented magnetic fields, but in this case it's representing an electric field. The electric field means that if it's crosses, then they are going to go in the page. So this electron is going to experience a force towards a positive plate, which is sort of out of the page, towards you as you read it or as you watch this. So that's fine. So we know that the electrons are going to be experiencing a force towards us. The question, of course, is how strong is that force? And the most important thing is how strong will a magnetic field be and a direction in order to account for that so that the electron beam is undeflected. Well, the important thing here is that QVB, which is the force due to the magnetic field, must equal to the force due to the electric field. And if you rearrange that, you get V is equal to E over B. And if you work that out, what you end up getting is a magnetic field of equaling 1.9 by 10 to the power of -4 Tesla. That's fine. That gives us the strength of the field in order to this electron beam to be undeflected. But of course, what is the direction of the magnetic field so that this is true? Well, again, understand, we want a force that is opposing the electric field's force. And as I said, the electric field is coming towards us, so we want a force that is going into the page. Well, my current will be going in that direction because it's opposite to electron flow, so my magnetic field lines will have to go up the page in order to do that. So there's your answer. Magnetic field lines that are going up the page with a size of 1.9 by 10 to the power of -4 Tesla. Question 24. This is a similar question to a number of years ago. Question I recognized as soon as I saw it, but it's a little bit different. It says, explain the shape of this graph in terms of the behavior of the electrons in the metal. So we're interested in the behavior of the electrons, okay, above and below. So let's talk about above. So above, of course, we're looking at this section right here. What's going on over here? Well, above, of course, you need to understand that electrons are flowing through a metal. And if they're a metal, we have a lattice. But of course, the atoms of this lattice are vibrating. We refer to them as the phonons. And of course, what happens is that the electrons are free to move in the conduction band. The conduction band is where all the electron flow occurs. But unfortunately, the phonons cause collisions of the electrons and therefore slow them down, and that means an increase in resistance. And the more temperature we get, the more in collisions we get, and the more resistance we get. So therefore, that describes the curve. What about below though? Well, then below, of course, we have a sudden drop at the critical temperature. You need to refer to it, of course, because it's mentioned in the question. So below the critical temperature, we have very minimal phonon interactions. So much so that electrons will distort the lattice. Well, that, of course, leads to development of a Cooper pair. And that ties us understanding into BCS theory. And of course, that Cooper pair means you get two electrons going through the lattice unimpeded and therefore no resistance whatsoever. Question 25. So question 25 is all about understanding graphs and about the scientific skills of interpreting graphs. And so in this question, we're dealing with two teams who determine the relationship involved with masses involving with Newton's law of universal gravitation. So they do the same procedure and accurately measure the gravitational force between two spherical masses over a range of distances. And as you can see, we've got two different graphs. And the first question says compare qualitatively the relationship between the force and distance in the graphs and assess the appropriateness of Team A's data and Team B's data in achieving the purpose of the experiments. So let's look at part A first. So when we look at part A, it says compare qualitatively. So we're not really interested in the numerical value. And secondly, it's important, it says in the graph. So you need to look at the relationship between the force and the distance in the graphs. So if you look carefully at the actual results, you can see that Team A has actually only 4 data points. But they've determined those data points over a distance of almost up to 2.2, 2.3 meters, and actually has a quite range of masses and so forth. Team B has a lot of more data points, and as you can see, it's got 8 data points. But in this case, all 8 data points are anywhere between 0.4 meters and 0.5 meters, so it's a much narrower range. So when we look at comparing the qualitative relationship, you can clearly see that Team A's have established an inverse relationship. Now, we all know that, of course, it's an inverse square relationship. And if you did further analysis by graphing the relationship in terms of the distances, it's a distance squared, you might get a straight line. But in terms of the inverse relationship, it's clearly the case that there's an inverse relationship here. With Team B, the results seem to indicate, at least in terms of their results, a linear relationship, in fact, a negative linear relationship. And so that's all you need to do. Compare qualitatively your relationship. Team A has got an inverse relationship or an inverse square relationship. Team B has a negative linear relationship. And that was all that's required because you've done it for both graphs. Question part B is assessing the appropriateness of Team A's data and the Team B's data in achieving the purpose of the experiments. As you know, assessing is coming up with some sort of judgment at the end, and that's really important. So Team A, as I already stated, has only 4 data points, but they've clearly established an inverse relationship. Whereas Team B, because of the narrowness of data, they actually don't get the sense of an inverse relationship. For all we know, this data point can actually continue along like this. And these data points are actually part of a much larger graph, which would establish an inverse relationship. So Team B's results actually isn't very good because of the narrow range of distances that they've utilized. So in answering the question, you would say, okay, 4 dot points here, 8 dot points over here. One would first say this may be a bit more valid. But in fact, the larger range of distances allows someone to actually make the assessment that Team A's results are better in terms of the purpose of the experiment. And so that's probably what you need to do for the 3 marks, is to say what Team A is doing, say what Teams B are doing, and then making the assessment. Question 26. I won't spend extended a lot of time on question 26. This is a question that comes up time and time again. It's worth 5 marks. It says explain how applications of transformers have affected the society. Now again, it's about explaining. So that's all about cause and effect. So we're looking at applications of transformers affecting society. So you need to talk about applications of transformers. You can't just say transformers. So applications of transformers could be the fact that we have a lot of medical devices that need step-up voltages to work. So for example, an X-ray machine, MRI machine probably need step-up transformers. We can then all talk about applications such as computers. They need step-down transformers, and that's really important as well. But then now we've got the applications, and we're looking at both step-up transformers and step-down transformers. You need now to say is how they have affected society. Well, we know that medical devices will increase the lifespan of people because we've got early diagnosis and so forth. But it's affecting society. So the point is that increased lifespans can be a positive effect, more productivity to society, but it can also have a negative drain on the financial aspect of society because of the fact that there are now more people who may be on pensions and so forth. So there's a negative aspect on society. If we're talking about computers, again, the analysis of technology means more leisure time, more automated tasks, so therefore people have more free time. You could say that's a more positive outcome to society, but you could say, look, more leisure time means less labor intensive tasks and people will get more obese as a result. So you could argue that application of transformers have had a negative aspect of society, but notice I'm talking about cause and effect in terms of the applications, how they have contributed to society's betterment or society's decline. Question 27. Question 27a is all about Hertz, and it says outline observations that Hertz have made were consistent with the photoelectric effect. And in your answer, identify the equipment that was essential for him to make these observations. Now you should know something about Hertz's experiments, and that he basically had a spark generator which produced a spark. And of course, we know that over here we had some sort of detector, and we know that it produced a EMR, a radio wave, and he was able to establish that the speed of this radio wave was c, so that was an example of EMR. And by the way, I've mentioned the fact of 2 bits of equipment that he's used, the transmitter and the receiver. But what's really important is that he put a box around this in order to see the sparks more clearly. Now this box had a glass window, and he noticed that the glass window actually caused the spark distance actually to decrease. In other words, it wasn't very strong. And then we all now know that that glass is opaque to UV, and therefore the presence of UV, which was actually due to the result of the spark produced over here, caused the photoelectric effect and an increased spark length over here. When he replaced this box with a quartz window, he noticed that this issue was resolved. In other words, the spark length was longer. And that's because, of course, as we now know, that quartz is transparent to UV. So UV was allowed to be passed through this box, and so therefore we had greater emission of electrons, as we now know. So you can clearly see I've now identified the equipment that was essential to make these observations. Part B, it says explain how the result of one investigation of the photoelectric effect changed the scientific understanding of the nature of our light. So one investigation. So did you do an investigation in class, or did you do some sort of animation, or is it an investigation in terms of actual historical investigation? I think it's more of the former, an investigation that you've done in class. And you would have noticed that, for example, if you have a solar cell and let's say this represents my solar cell over here, and allow red light to hit it, then I might not actually get a current to flow in a circuit that is based on that. So in that case, we all know that is because the frequency here is too low. But if I then fire blue light at it, I might get current to actually flow simply because photoelectrons are emitted from this solar cell. And so what that does, so that's the investigation, but now we need to talk about how that changed our scientific understanding of the nature of light. And of course, our understanding of nature of light has changed from a classical model to a quantum model. And what that means is that the classical model says that energy is a continuous wave, but a quantum model says that light actually behaves in a particular way, or it behaves like particle nature. And we all know now that means photons. And those photons, of course, each photon has the energy equal to hf, and that explains this observation over here. So as long as we have one photon that has the minimum amount of energy, we cause the electron to be emitted and therefore produce a current. And the fact is that changes their understanding of light. And of course, this all ties in with Einstein's understanding of the photoelectric effect. So you've got to look at the cause and effect, explain. You're looking at the observations of how certain frequencies of light don't cause a current in a circuit involving a solar cell or a photocell, but higher frequency light does. And changing the intensity does not affect it. So for example, you may have actually had red light and really increased the intensity, but still got no current in the circuit. Well, that shows you, again, the fact that the photoelectric effect states that it's about the actual frequency and hence the energy of the photon, not the number of photons. So if you have one photon that doesn't cause an electron to be emitted, increasing the intensity will therefore not make any difference. All you do is increasing the number of photons, but the actual energy of each photon isn't changed. So you can see I'm tying in the investigation, I'm tying in the observations to our understanding of the nature of light. Question 28. So question 28 is a 5-mark question, and we need to, it says, explain the acceleration with reference to the law of conservation of momentum. Now we all know conservation of momentum. Conservation of momentum simply says that the total momentum before equals the total momentum afterwards. So in the beginning we have a total momentum equal to 0, that is before it's launched. Well, as the rocket is launched, of course, we have gases spurting out at all points out of the journey, and as a result, of course, the rocket moves forward, and that's of course Newton's third law. But how does this apply to conservation of momentum? Well, of course, the amount of gas being emitted is constant, but of course what happens is that the rocket is decreasing in mass. So it's not staying the same as you would normally see in any equation, it's actually decreasing in mass. So the mass is decreasing. Well, because of conservation of momentum, that means velocity has to increase as a result, because generally you have your gases here, same mass overall, but the mass is going the other way. You're going to have a velocity out the back fairly constant. So in order for conservation of momentum to be true, the mass decrease here means velocity increasing. That's the first aspect. So the conservation of momentum can explain why we have an increasing acceleration, because the velocity increases as the mass decreases. But the other component to look at is the fact that we are moving further away in Earth's gravitational field. So the acceleration due to gravity here is 9.8, and that is what the rocket has to overcome. But over here, the acceleration due to gravity here may be only 7. And so therefore, we also have the effect that we also have the fact that a decreasing acceleration due to gravity will ultimately mean that the force on the rocket over here will have a greater effect. And so therefore we have a greater acceleration as well. So I've explained the acceleration of the rocket, and I've referred to the conservation of momentum, but it's a 5-mark question. So no doubt there will be some sort of marks allotted to the understanding of gravity as well as our conservation of momentum. Question 29. It says explain how different discoveries in physics led to the development of 3 technologies, including an electric generator. I'm not going to go at length to this particular question. It's worth 6 marks. So one could surmise 3 means 2 marks each. So you're really looking at a discovery and, of course, cause and effect that leads to a technology. Now, you already talked about a technology including the electric generator. So you've got the generator. So you need to refer to that. Well, the discovery, of course, is all to do with Faraday and his development of Faraday's law and how a moving magnetic field will generate an electrical current. So you need to talk about that. But what are some other technologies that lead to different discoveries? Well, you could lead to Onas's discovery of superconductivity. That leads to the whole things of maglev. You could talk about that, MRI machines and so forth. You could talk about J.J. Thomson in terms of discovery of the electron. And of course that leads to cathode ray oscilloscopes and cathode ray tubes and TVs and the like. You can talk about the BCS theory and in terms of semiconductor. And of course that leads to computers. So you can see there's a whole host of options available to you. This is actually all part of assessing one of the PFAs, which is the prescribed focus areas. And the last question. And the last question involves the generation of electricity by having a rope pull a pulley, which turns a magnet or some sort of rotor, which produces a current and therefore lights the light bulb. And in this case, you are asked to calculate the maximum possible energy released by the light bulb as the mass falls through the distance of 1 meter. Well, if the mass falls a distance of 1 meter, then we have a loss in potential energy. So the potential energy goes down. That means we have to have an increase of electrical energy, which of course is what we have to work out. But how would you work out the loss in potential energy? Well, basically it's potential energy final minus the potential energy initial. The important thing is working this out, you cannot use MGH. For starters, this is involving Mars and not Earth. So how would you work out the final potential energy? Well, as you know, the final potential energy is a position at negative G m1 m2 over r minus another negative G m1 m2 over r. Now what are these values? Well, G, m1 and m2 are already known. So we know the mass over here. We already know the mass over here. So that's these two masses here. G, of course, is a constant. And what is r? Well, r is related to this value over here, and it's already conveniently placed in meters. So this initial one over here is that value over here, which is 3376204. Right? Whereas the final one is a bit lower, and that is equal to 3376203, because it's dropped down a distance of 1 meter. So if you do the calculations, and I won't go into the details here, but if you did the calculations correctly, you'll get a value of 7.47 joules to 3 significant digits. So that's the amount of energy going through this light bulb, and basically that's what you would have to do for the 3-mark question. The last part is explain the difference in the behavior of the falling mass when the switch is open. So that begs the question, what's the behavior if the switch is closed? Well, if it's closed, you're getting a current in here. And so what's happening is this mass is falling, and you normally say, well, it's accelerating, but it can't accelerate because the faster it turns, the more what we're going to get here is a level of retardation because of the fact of Lenz's law. Because you're going to get a current developing in the generator over here, which causes this not to spin at a accelerating rate. It's basically you're going to get Lenz's law act. So basically when it's closed, it should fall at a constant velocity, and you need to explain, of course, this, and that's because of Lenz's law. But if it's open, what's going to happen? Well, all of a sudden we no longer have a current. So there's no current going through the generator here and through the light bulb. So Lenz's law is no longer at play, and now it should accelerate as it drops. And now I've explained the difference between the behavior of the falling mass when the switch is open. Well, that was the HSC in 2016. I hope that has made sense to you. Thanks for watching. Bye for now. I hope you found that video useful. And remember, like, share and subscribe. Oh, and if you have a comment or a question, or you'd like a concept for me to explain to you, please drop a comment down below. I'm Paul from High School Physics Explained. Bye for now.